All right, so let's take a look at page 333, number 15. Okay, so here they give us two vectors and they give us their magnitude. So magnitude of A is equal to 3, magnitude of B is equal to 5, and they give us the sum of these two vectors, just give them their magnitude at least, okay? And that is equal to 7, and they want us to determine the magnitude of A minus B, okay? So this is yet again one of these questions where a really good diagram is going to be helpful here. So let's put down what we're looking for. We're looking for A minus B. Okay, so let's say this is A and this is B. Okay, so here we have 3 and 5. And so what we're looking for is the magnitude of A minus B. Okay, so from the second to the first, this is what we're looking for, but the information that's given is A plus B, okay? So for A plus B, I have to move one of these vectors tip to tail. So I'll choose to move this vector with length 5 over here. And then this gives me the vector A plus B, which has a magnitude of 7. Now, what are we going to use? What are we going to use this for? Well, what I'm hoping to find, if I'm looking for the magnitude of the subtraction, is the angle between the vectors. So I'm hoping to find angle theta, but because they're giving me the sum of the two vectors, the angle that's not equal to theta but related to it would be this supplementary angle, which I call phi. Okay. So again, we've seen this many times where the angle between the vectors is not necessarily the one you're going to be working with, in this case here, when you're working with addition. Okay, so any questions on that? So to find phi, I'm just going to use the cosine law. Okay, so cos inverse of its opposite side is 7, so it's 7 squared minus 3 squared minus 5 squared all over -2 times 3 times 5. Okay. And I think I'll just make my life simple and do everything to 1 decimal place. Okay, make sure you're in degrees, cos inverse of, so what do we have? We have 49 minus 9 minus 25, and then divided by -2 times 3 times 5. And it looks like, always the nice angles with this book. Okay, so that angle phi is 120 degrees, which means that theta is 180 minus 120, so 60 degrees. Okay. And so now that I've got this angle, I can now solve the triangle of interest, okay, which is the one that contains the subtraction. So I'll use cosine law again, except now knowing this angle theta. Okay, so the magnitude of A minus B is just going to be equal to the square root, and I'll just apply the cosine law. So 3 squared plus 5 squared minus 2 times 3 times 5 times cosine of the angle between the vectors, which now I know is 60 degrees. And I know I could probably find a more exact answer, but I'm just going to find it to 1 decimal place to keep things simple here. Okay, so here we have the square root of 3 squared plus 5 squared minus 2 times 3 times 5 times cosine of 60. And it looks like I have about 4.36 or 4.4. Okay. And the idea here is about understanding the relationships that are involved. Okay. The difference between the relationship with two vectors placed tail to tail and their subtraction, and then working with those two vectors tail to tail with the addition, placing them tip to tail, and understanding the relationship between these angles. Okay, so are there any questions on this one here? No? All right, so let's move on. Okay, and what I'm hoping you're seeing when I'm doing these questions is how I'm just applying. There's nothing special here. I'm just applying what we know about addition, subtraction, getting it down in a good diagram. Okay, so I think next we're going to go to 344. Okay. So 344, number 9. Okay, so it's actually on page 345. So here it says, given these three vectors, express each vector as a linear combination of the other two. Now, I believe this one here, I gave a very specific combination. I didn't ask for you to do all three. So can somebody remind me which combination I asked you to do?
I believe it was just P relative to R and Q.
Okay. So this is number 9. So we're going to write vector P as a linear combination of vectors R and Q. And of course, a linear combination involves two possible operations. So I can multiply the vectors by a scalar multiple, and then I can add them together. Okay. But of course, they're giving me specific vectors here. So if P is -11, 7, I want to write that as some scalar multiple of -3, 1 and -1, 2. And so what we have is an equation with two variables in it. And so we should expect to be solving a system of equations. Okay. And of course, step number 1 in any equation is simplify to a form that's a little more usable. And in this case here, a more usable form is to have the equality of two vectors. So here, this is -3m minus n. Now you might choose to do this in 2 steps, but I'm going to do it in 1 step because I've got, 9 people here watching me. So you should find any errors. And then 1 times m plus 2 times n. And now that I have the equality of vectors, I know that the x components have to be the same. So -3m minus n has to be equal to -11. Okay, and I know that m plus 2n has to be equal to 7. Okay, and you solve this as you like. This will be fine in using substitution, but I'll use elimination. So I don't know, I'll multiply the top one by 2, I guess. So here we have -6m minus 2n equals -22. And then here we have m plus 2n is equal to 7. That doesn't change. And here we're going to add them together. So -6 plus 1, -5m is equal to -22 plus 7, I guess, is going to be -15. And so m is equal to 3. Okay. And then we are going to look for n. So I'll use that one up there. So -3 times 3 minus n equals -11. So n is equal to -9 plus 11. That looks like it's 2. Okay. Now, technically, this is not the answer because the answer is to write P as a linear combination of Q and R. So that linear combination is going to be 3Q, okay, plus 2R. And of course, like a lot of equations, you can check your answer by sort of plugging everything in. I'm not going to do that. I'm going to hope that I got the right answer. All right. Any questions on this one here? So it's very important to understand that, understand what we mean by a linear combination of vectors, and to understand that in most cases, you can use vectors in 2D or 3D. Okay. So the first step, somebody asked how I got the first step. This is what it means to be a linear combination. Okay. So linear combination is like a linear combination of the variables x and y would be like 2x plus 5y. So as long as my variables don't have any exponents to them, and it just involves multiplying by some constant, then this is considered a linear combination, and it's very similar to vectors. When we talk about a linear combination of vectors, we're talking about being allowed to multiply those vectors by scalar multiples and then adding them together. Okay, does that answer the question? Okay, so that's why, it's always good to have a quick look at the notes, even if you're not necessarily, making your own. It's a good idea so that you kind of see what all the definitions are. All right. So I believe on this next page, so some person asked for 10A and somebody 345 number 10. Okay, just number 10 in general. All right, so let's take a look. 345. So here, page 345, number 10. Okay. So it says, find an equation to describe the set of points equidistant from the two given points. Okay, so the given points are 2, -1, 3. And the other point is 1, 2, -3. And we're looking for points. So these are things I don't know yet. Okay, so I'm going to give them some sort of name. Okay, so I'll call the point that I'm looking for, I'll call it X, Y, Z. Okay, and I need the distance between A and P and the distance between B and P to be the same. Okay, so if I don't care where these points are in 3D, but I've got some point P that I'm looking for, and then I've got two given points, A and B, and I need the distance between A and P to be the same as the distance between B and P. Okay, and the way in which I can work with this is not thinking about distance, but think about the magnitude of the vector that's produced when I join the points in question. So essentially, for those distances, to be the same, I need the magnitude of AP, the vector AP, to be equal to the magnitude of the vector BP. So notice here, it's not the vectors themselves that are equal, because clearly they're not necessarily pointing in the same direction, but it's just their magnitudes that are going to be equal. Okay. Now, you might ask yourself, that seems odd to draw it so that they both end at P, but recall that my reasoning for doing that is that the way in which we find the vector joining two points is to subtract the second minus the first. And if I go from A to P, when I do that subtraction from second by first, I always end up with my variable components that come first. It's the only reason for doing that. So let's find the vector AP. So X minus -2, X plus 2, Y minus -1 is Y plus 1, and then Z minus 3. And I'm finding the magnitude of that vector, and then the same thing for the vector from B to P, X minus 1. Oops, I shouldn't have, it's just a comma there. X minus 1, then Y minus 2, and then Z minus -3, which is Z plus 3. Okay, and of course, the way in which we take the magnitudes of vectors is the square root, and it's the sum of the squares of all the individual components. So X plus 2 squared, the X component, plus the square of the Y component, plus the square of the Z component. And then similarly here, square root of X minus 1 squared, plus Y minus 2 squared, plus Z plus 3 squared. Okay, so again, despite the fact that this looks very complex, I'm just applying the definition of the magnitude. There's absolutely nothing special going on here. Okay, so now I'll square both sides of this equation to get rid of the square roots. And while I'm at it, I'll expand all of these binomials. So X plus 2 squared is going to be X squared plus 4X plus 4. It's going to be Y squared plus 2Y plus 1. This is going to be Z squared minus 6X plus 9. And same thing here, X squared minus 2X plus 1. Y squared minus 4Y plus 4. And lastly, Z squared plus 6Z plus 9. And as we saw in the very similar example we did in class, all the squared terms cancel out. The Y squareds go and the Z squareds go. And so all I'm left with are terms in X, Y, and Z, and some constants. Okay. So let's take a look here. We've got 4x, and then I'm going to bring that over to the other side plus 2x. So that'll be 6x. Let's see, 2y. And then here I've got a negative 4y. So 2 plus 4 is again 6. So 6y. And then what do we have here? We have, oh, nobody noticed that. That should have been 6z, not 6x. Okay. And then here I have negative 6z minus another 6z. So that looks like minus 12z. And again, I hope you're keeping track of my work here in case I made a mistake. So here, 4 plus 1 is 5, plus 9 is 14. And I'm subtracting 1, so 13 minus 4 is 9. Then minus 9 again. Oh, looks like all the constants canceled out. Okay. If anybody sees an error, just take a quick look, make sure I did that addition correctly. Okay, if I was doing this on a test, I probably would have brought in my calculator. Okay, and I can even simplify this. If I divide both sides by 6, I end up with x plus y minus 2z equals 0. Okay, so if I'm looking for an answer, it's not one particular point that is equidistant to both a and b. This represents infinitely many points. And in fact, they gave us that idea that said, find an equation to describe the set of points. Okay, and there's infinitely many points, and you could sort of imagine, because that point is also equidistant, and this point is equidistant, and that point, there's infinitely many points that are equidistant to a and b. Okay, so in B now, so this was part A. In B, they say find the coordinates of 2 points that are equidistant. Okay, so it looks like there's a question or there's a hand up. Yeah, Mitchell.
I just checked the back of the book. I mean, it's wrong sometimes, but it's saying x minus 3y plus 6z is the answer, equals 0.
Oh, let's take a quick look here on the y's here. So we've got 2y, and then here we had minus 4y. So 2 plus 4 is 6. Did I write these things down? So this is y plus 1. So that looks okay. And then here y minus 2. That looks okay. And did I write down the points correctly? Okay, 2, negative 1, 3. 2. Oh boy, look at that, folks. You have to help me out here. This should have been plus 2. Okay, so I'm just going to solve it as it is. And with this here, this should have been 2, negative 1, 3. Again, I was hoping, when I make these kinds of mistakes, I kind of need some help here on this. Okay, so I'm just going to solve it as is. Obviously, it will be a different answer. That should have been a positive 2, not a negative 2. Okay, but the idea is the same. Okay, so sorry, I didn't notice that where nobody else did. Okay, so here they're asking me for 2 specific points. Okay, here I could find as many as I like. Now I would say do stuff that's easy, well, pick what if x is 0 and y is 0. Okay, well, hey, these 2 things disappear, and lo and behold, what is z going to be equal to? 0. So 0, 0, 0 is actually one of my points. And I could just keep doing this. Let's say x is equal to 1 and y is equal to 2. I don't know, just I could pick anything I like. So what happens here? We have, 1 plus 2 is 3. Okay, so we have 3 minus 2z equals 0. So z would be equal to 2/3. So there's another point, 1, 2, 2/3. Now at this point here, I might sort of think, say I had to find more. I realize, you know what? I probably should leave one of the ones that don't have coefficients other than 1 in front of them. So I don't have to work with, fractions. So maybe what I might do is I might take y equals 1 and z equals 1. And what would that leave me here? Well, x, 1 minus 2 is -1. There you go. X equals 1. And there's another point. 1, 1, 1 is another one. And I could just keep creating more and more points. Okay. By just choosing, because remember, the only thing that has to be observed is that this equation is true. This is the equation that ensures that this XYZ point is the same distance to either of those. Okay, so obviously the ones for the actual questions won't be correct because the actual question had this is positive too. Okay, but is there any question about the process here? Okay, all right, so let's move on. So that's done. So somebody asked for number 18 in this one here. So did I assign both 18A and B, or did I just assign 18A? Because 18B really is almost identical to 345 number 9. So it's the same thing because it's asking you to write a vector as a linear combination of two others. All right, so I think I'm going to leave B, okay, because it's just a little too simple, a little too similar. You can just adapt what I did in the other problem. So we'll just look at A, okay, and it says explain why the vectors 2, 3 and 3, 5 span R2. Okay. So when we talk about, if you look at the notes, when they talk about spanning R2, essentially they're asking, are these two vectors, let's give them names, let's say U and V, they're essentially asking, are U, whoops, they're not necessarily unit vectors, are U and V what we call basis vectors? Okay, meaning can these two vectors be used to write any other vector on the Cartesian plane in the same way that we used, in the same way that in this question, we were able to use -3, 1 and -1, 2 to write -11, 7. And we could have done that with any other vector in R2. And so there are two conditions that have to be met. So in this case here, the answer is yes. Okay, but why? Well, because number one, neither is the zero vector. Okay, so you can't have the zero vector as one of your basis vectors. And anybody remember what the other restriction is on being a basis vector?
Can't be collinear.
There you go. Can't be collinear or parallel. Collinear, parallel mean the same thing. Okay, so whichever word you use, okay. Okay, so U and V are not parallel. In fact, if you don't remember the term, you could just say U is not equal to a scalar multiple of V. And that would be something pretty easy to check, because if I had to multiply the X component 2 to get 3, I'd have to multiply by, okay, 3/2. But clearly 3 times 3/2 is not equal to 5. They're not scalar multiples of each other. So these are the conditions for two vectors to be basis vectors, which then allows you to use them to span R2. This just means that you can use these two vectors, okay, or linear combinations of these two vectors to write any other vector in R2. Okay, and then part B is just a question very similar to the one we did. All right, any questions on these two conditions? No, okay. All right, so I think we're done with those pages. So let's go to 348. All right, so 3, 4, 8, I see 2C. Take a look at 2C.
Sorry, is it okay if I
Yep.
just see a bit more from like the end of that question above, because I'm missing just a bit of it. Yeah.
So here, the two conditions is you can't have vectors that are the 0 vector that can span R2, and they can't be parallel to each other. Okay, because if I try to add scalar multiples of vectors that are parallel to each other, I just get another vector that's parallel to those two. So clearly that's not going to help me get some other vector on the Cartesian plane. Is that okay?
Yep.
Okay, great. So 348, 2C is saying, so they give us these 2 points and they want us to find a unit vector in the direction of BA. Okay, so here, let's take a look at the points they give us. So let me try to write them down correctly. Please check, folks,
Sorry,
this time.
My textbook doesn't have this question. It only has,
348, 2C.
yeah. It only has A and B.
Oh, well, there you go. You got some earlier version of the textbook, I guess. I guess I'll let you skip that one. So you can follow along then, Elliot. That's odd, but maybe they added it in. It's pretty weird. So you might just have a later version, an earlier version of the textbook. Sometimes that happens. Okay, so you can just follow along. So -2, 3, -5. And then B is 6, 7, 3. Anybody else in that situation? Out of curiosity? That's very weird. Okay, so here it says they want a unit vector in the direction of BA. Okay, so if you're looking for a vector that's in the same direction of some other vector, then it means you're going to have to do a scalar multiplication, because that's the operation that automatically gives you parallel vectors. Okay, so the first thing I would do is I would calculate the vector BA. Okay, so remember BA is second minus first. So in this case here, you're going from B to A. So it's going to be -2 minus 6, -8, 3 minus 7, -4, -5 minus 3, -8. Okay, so this is the vector that goes from B to A. All right, and now you want to find a unit vector in that exact same direction. And what we saw was that if you multiply by 1 over the magnitude of the vector, it automatically produces a unit vector in that same direction. Okay, so what we're gonna have to do is find the magnitude. So what do we have? We've got 8 squared plus 4 squared plus 8 squared. So notice here, I don't even bother with the negatives because I know I'm going to be squaring them. So won't be any difference because of that. So here, let's calculate this. So what do we have? We have 64 plus 64 plus 16 and 144. Hey, look at that. It's even a nice number, because obviously the square root of 144 is just 12. So it's 112, 1 over 12 of -8, -4, -8. And, you know, in principle, it would be good to multiply that in. So it looks like that'll be -2/3, -1/3, and -2/3. Okay. So 2 things going on in this question. Number 1 is, how do we find the vector that joins 2 points? Okay, so obviously the order matters, because if you do A to B or B to A, they'll have the same magnitude, but they'll be opposites. So step 1. And then step 2, how do we create unit vectors? We multiply by 1 over the magnitude. Okay. Any questions on this one here? No? Okay. let's go to number 4. So here it says this is 3, 4, 8, number 4. All right, and what are they asking for here? They're giving us 2 relationships between vectors. They're telling us that 3x minus 2y, that this combination is equal to the vector A, and then 5x minus 3y is equal to the vector B. And they're asking us to write x and y in terms of A and B. Okay, so essentially what we're doing is we have A and B given as linear combinations of x and y, and they want us to flip that around. Okay, and what I'm going to do here is I'm going to treat them essentially as a system of equations, because vectors satisfy distributivity and commutativity, which mean that we can treat them like systems of equations. All right, so here I'm definitely not going to use any kind of substitution here, because I don't want to deal with a whole bunch of fractions. So it looks like I don't know, probably easier to multiply the y's. So I'll do 3 times equation 1, which gives me 9x minus 6y equals 3a. And then here I'll do 2 times equation 2, which will give me 10x, okay, minus 6y equals 2b. And you see how I'm treating it exactly like a system of equations. I'm going to subtract them, because I know that negative 6y plus 6y is going to give me the 0 vector. Excuse me. And here 9 minus 10 is going to give me negative x. Is going to be equal to 3a minus 2b. And so x is going to be equal to negative 3a plus 2b. Okay, and there you go. I've written x as a linear combination of a and b. Okay, so now at this point here, I could do one of 2 things. I could either replace this back into one of the equations, but then have to deal with moving things around. But just to show you another thing that I could do here is I could just start over and eliminate the x's, and all I'm going to left for y. So again, just to do something a little different here, let's do 5 times equation 1 and 3 times equation 2. So what do we end up with? We have 15x minus 10y is equal to 5a. And now let's multiply the second one by 3. 15x minus 9y is equal to 3b. Okay. And now here I'm going to subtract again. So what do we have? 15x minus 15x gives me the 0 vector. Negative 10 plus 9 gives me negative vector y. And this gives me 5a minus 3b. And again, I can just divide or multiply both sides by negative 1 to get y equals 5a plus 3b, or negative 5a plus 3b. Okay, so an alternative to doing a substitution. And we see here how we can use the fact that these things are associative, distributive, and commutative to treat them just like they were polynomial expressions. Okay, so any questions on this here? Okay, so it looks like we can skip 7, so that's good. So 377. Let's go to 377. All right, so let's take a look here. This is a short question, so I got space here. So here we have page 377, number, this is number 2. Okay, and it says here, explain why the calculation A dot B and then dotted with C has no meaning. Okay, so let's take a look here. Well, I know that when I'm, doing algebra, I always do what's in the brackets first, okay, unless I have some rule that allows me to not do that. And the first thing I realize is that A dot B gives me a scalar quantity. And then here, that would mean that I would be trying to do the dot product between a scalar and a vector quantity. And this is where we see that this is meaningless, okay? Because dot product or scalar product is defined as being between two vectors. Okay, and so this is why I cannot perform this dot product. Okay, because even if you think of the algebraic definition of dot product, I need to have an x component in both to multiply and a y component in both to multiply. A scalar does not have x and y components. And from a geometric perspective, I need the angle between two vectors in order to calculate the dot product. And of course, a scalar quantity has no direction. Okay, so the fact that that first operation that you perform produces a scalar quantity, you then realize that you cannot take the dot product with that vector quantity. Okay, any questions on that one? Okay, folks, I apologize for going so fast, but I do have to see if I need to get back to the reach for the top finals. So I do need to go a little fast here. All right, so next we've got number 11. Okay, so page 378, number 11. And let's see what they give us here. So they tell us that A minus 5B, this linear combination of vectors A and B, and this other linear combination of A and B, just A minus B, so that these two, now remember, when I subtract vectors, I get another vector. They said that these two vectors are perpendicular, okay? Now, they also tell us that A and B are unit vectors. Now, because the textbook doesn't use the hat notation, they have to specifically tell us that two vectors are unit vectors, okay? And then it says determine A dot B. Now, problem here is that I don't really have that much information about A and B. I know they're unit vectors, okay? So I don't have them given algebraically, so that's not really going to be helpful to me. All right, so the only thing I really have to work with is that these two vectors are perpendicular. And as I mentioned to you earlier, as soon as you hear two vectors are perpendicular, what you need to be thinking now is that the dot product of those vectors are perpendicular. Sorry, that the dot product of those vectors is equal to 0. Okay, the vectors are perpendicular, hence their dot product is 0. And what we have to hope is that this piece of information, along with the fact that A and B are unit vectors, is going to be useful for us. Okay, and maybe if you think about what happened when we took the dot product of these combinations of vectors, maybe you'll see where this is going. So let's simplify this. Hopefully it'll be useful. So here we just distribute like we do with algebraic expressions. So that's going to be A dot A. And then here we have minus A dot B. And here we have minus 5B dot A. And then lastly, we have plus 5B dot B. But here I have a vector dotted with itself. We know that's equal to the magnitude of the vector squared. Of course, it's a unit vector, so that's just going to be 1. Here, these two expressions are equal to each other because A dot B and B dot A are the same. So this can just be rewritten as minus 6 A dot B. So I have -1 and then minus 5 of the same expression. And similarly here, B dot B is equal to the magnitude of the vector squared. And since it's a unit vector, oh, I forgot the equals 0 here. And look what we have is we end up with an equation where the only thing that's unknown is A dot B, but that's really good because that's exactly the thing we're looking for. Okay, so if we bring that to the other side, we get 6A dot B is equal to, well, 1 plus 5 is 6. Okay, and lo and behold, A dot B, I can now solve for, divide both sides by 6, is equal to 1. Okay, so notice here how I didn't actually need to find the angle between the two vectors, because the algebra that I was able to do by using this piece of information, the fact that they're perpendicular and that the dot product then has to be equal to 0, I'm able to use this algebraic simplification. Okay, so it's a nice little question because you're getting the answer indirectly, okay, using a property that, knowing that these two vectors was perpendicular ended up helping us to determine the dot product between two of their components. Okay, so sometimes, remember, don't necessarily assume you're going to know where a question is going. Just take the information you're given and see where it leads you. In this case here, it eventually led us to the answer. Okay, any questions we have on that?
I'm a little confused to how you got the third step, like 1 minus 6 vector A dot. Yeah.
Yeah, so here, A dot A, so one of the and in fact, this is one of the ones that you proved in one of the lessons, is we saw that if I take a dot product of a vector with itself, well, that's the magnitude of the first times the magnitude of the second, which is the same, times cosine of the angle between them. But what is the angle between two vectors that are in the same direction? It's just 0. And so here you have the magnitude of u squared. And what's the cosine of 0? It's just 1. But here, what did they tell us? So A dot A would be the magnitude of A squared. But what did they tell us about vector A? It's a unit vector, meaning it has magnitude 1. And similarly for B dot B. B dot B is the magnitude of B squared, but the magnitude of B we were told was equal to 1. Okay, does that answer your question?
Yes, that makes sense. Thank you.
Okay, great. Anything else on this one? Okay, so I think there's one left here. So 386, number 10A1. Okay, so this is page 386, number 10A1. Okay, give me just a second here. Okay. It says for vectors A and B, determine the values of P and Q so that the vectors are collinear. Okay, so here, let's take a look at the vectors that they're giving us. So vector A is given by 2P8, 2P8, Okay, so we notice here there's an unknown quantity in there, and then vector B is given by Q 4, 12. Okay. So in 10B, it asks you or part 2 asks you to determine what values of P and Q make these things perpendicular. Okay, so you would just use what we saw earlier. You would take the dot product, make it equal to 0, and then see what happens. Here, they need to be collinear. So remember, collinear, again, if you check the notes, collinear is the same as parallel. Okay, and what does it take for two vectors to be parallel to each other? Means they have to be scalar multiples of each other. So A, or I'll write it the other way around, looking at the numbers here. Okay, so vector B needs to be some scalar multiple of vector A. Okay, so in other words, 2P8 needs to be equal to, K times Q times 4 times K and 12 times K. Actually, I should have probably done it the other way around, but I could do it either way. Okay, so this is what must occur. Now, the reason why this is sort of solvable fairly easily is that means the X component of the right-hand side has to be equal to the Y component of the left-hand side. Okay, now there's one of these in particular that's going to make our lives very easy. Look at that. Okay, 8 needs to be equal to 12K. When I look at the X components, I see 2 variables. When I look at the Y components, I'm stuck with 2 variables. But when I look at the Z components, I'm only working with 1 variable. So 8 needs to be equal to 12K. And so K needs to be equal to 8 over 12, which is 2/3. Okay. And this now is going to help me solve, I believe, for specific values of P and Q. So do you see that in order for the Z components to be equal, K has to be equal to 2/3. So now when I look at the X components, 2 needs to be equal to 2/3 times Q. And lo and behold, I can solve for Q. Okay. So I just multiply the other side by 3 over 2, and I'm going to end up with 3. So Q has to be equal to 3. And similarly for the Y components, P is going to have to be equal to 4 times, again, 2/3, because I've established that the K value has to be equal to 2/3. And so here we have 8 over 3, and there's my P value. Okay. And those are the only answers. Okay. I suspect in part 2, when you're looking for perpendicular ones, I suspect that you might get a scenario where there's more than one possible answer. Okay. So here, the idea was to recognize that being collinear was the same as being parallel. And if 2 vectors are collinear or parallel, they need to be scalar multiples of each other. Okay. And then from there, from an algebraic perspective, it was noticing that those Z components allowed you to solve for an exact value for K. Okay, so nice little question. Any questions on this here? No. Okay, are there any general questions we want to ask about the test before we end off?
Possible for you to go over the 7 perpendicular as well?
Sorry, I missed that.
Would it be possible for you to go over the perpendicular part of the questions that are mentioned?
I'll do part 2.
Yes.
Oh yeah, sure. Let's do part 2. Yeah. So here they need to be perpendicular. So that means that A dot B is going to have to be equal to 0. So parallel means they're scalar multiples of each other. Perpendicular means their dot products have to be equal to 0. So here I'm going to take 2p8 and dot it with q412, and this dot product has to be equal to 0. So now let's perform the dot product. So 2p, okay, plus 4q. Oh, sorry, it's the other way around. 2q times 4p. Sorry about that. Went a little too fast. Plus 8 times 12 is 96. Has to be equal to 0. And notice here that you have a single equation with two unknowns. So what this tells you is that there's more than one answer. Now let's clean this up a little bit here. Let's divide both sides by 2. So q plus 2p plus 48 has to be equal to 0. Okay, so essentially all the q's and p's that satisfy this equation will produce perpendicular vectors. Okay, and clearly there's infinitely many of these. Okay, because if I pick q to be equal to 0, then p would be equal to -20 if I solve for it. If p is equal to 0, then q is equal to -40. So those are two different combinations of p and q, and you realize that, well, I could actually find a whole bunch of scenarios that satisfy this equation. Okay, as opposed to here where I was able to solve for a single value of p and a single value of q that made these two things be collinear to each other. Whereas here for perpendicular, there's actually infinitely many solutions. Okay, any questions on that there?
Is it possible to draw maybe like why would there be infinite number of perpendicular solutions?
Oh, first on 3D, it would be because the thing is, I guess that because you have an unknown in each one, I guess depending on how you choose them, there's probably can you imagine? Can you sort of see here? There's
Right.
by maybe changing one in each one, I might be able to create infinitely many perpendicular.
Right.
Obviously not as easy to visualize in 3D than it would be to draw something in 2D, but that's why it's good to kind of take and realize, oh, there you go, I got maybe there's some relationship that creates, you see how these things are all perpendicular to each other,
Yes.
even though I'm moving them around.
Yeah.
Okay,
Right,
anything
thanks.
else? Okay, so if that's it, I'm going to call it a day so I can go back and hopefully check up on the reach for the top people. Okay, take care, folks.
Thank you.
Thank you.
Thanks, Tony.
Okay, bye-bye.